Okay, in this section we will talk about the concept of frequency response. So, up to now, we have dealt with only transient plus steady state response. And so, in terms of unit, ramp, and parabola signal, but these signals does not contain any parts of the frequency. Which means that f is equals to the 0 at transfer function. Okay? Because it's not the sinus or cosinus signal. Assume that we have the mass spring damper system. Mass K and C. And also we have applied the F and X T. Okay? Then if we set the Ft is equals to the Ut, unit step signals, and so these signals gives us this kind of response. We know it if the system is stable. Like this one, okay? And so this part is the transient, this part is the steady state, right? Because we don't know anything about this one. And so this XS, which is given in here, K1 divided by S plus K2S plus K3 divided by S square Q zeta Wn S plus Wn square. And this is unit step signals. And this is transient, right? And so, firstly, K1 divided by S directly relates to what? The final response of this system. And so, it directly affects to the what? To the output of signals. If these have the frequency components, just like the sinus or cosinus, and so this system is affected. If you have the perfect controller, perfect transient and steady state response, if you apply this system with high frequency component of the inputs or the reference, and so your system may not catch the reference one, which we call it the frequency effect. Okay? This system is just like behave filtering. The filtering happens on that system right now if the input has the frequency components.
Assuming the frequency doesn't reflect on that. It blocks like a frequency.
Yes, it's just like the low pass filter is applied on this system.
So we do a frequency change if we want to, for example, if the output has a specified frequency different than errors, for example. So we can filter out the errors using that frequency, and then looking at the frequency of the output, we can.
In the PID controller, we stabilize the whole system based on what the frequency component is equals to the 0. But if you have the input signal with a frequency one, for example, f is equals to 10 hertz or the 100 hertz, and so if you have, even if perfect controller, your system cannot be response to this one.
So you have to redo the whole the calibrating thing for the PID with the frequency components in mind.
No, you cannot do that. You need to change the plant.
Okay.
That's only way to adjust it. It's just kind of the low pass filter, but based on what the MCK system. Okay?
So Professor, just to clarify this point, when we solved our systems before with PD and PI, we did not
Yes,
assume,
you have a perfect PID
we
controller.
didn't assume any errors from the frequency part.
You assume that the input signal has no frequency component.
Okay, the input is inside.
Okay? This is the basis of the low pass filter. And so at every system in the control system has the low pass filter. This analog. And so how can we write these conditions if we apply sinusoidal signal to GS? Ft is equals to the F0 times sinus Wt. Okay? And so we have the transfer function of Xs just like this one. Wn square divided by S square Q zeta W dot and Wn square times Wf0 and S square W square. Okay? What's this value? This is the what? The Laplace transform of these terms. Okay? And so, if you solve this equation, and then we will get this kind of response. Xs is equals to the what? K1s plus K2 S square W square plus K3 S plus K4 and S square plus 2 zeta omega ns and Wn square. This is related to what? The transient, right? But this is sinus right now. Okay? And so we have been affected by the frequency components right now. And so if we apply the input signal and we can generate the output signal. But if you apply the high frequency input, there could be change the output signal with the similar or reduced rate of this signal, just like the low pass filter in here, because your system does not respond under the high frequency components in here, even if you have perfect PID control. This is the result of the frequency solution of these systems. You get it? Okay. So, in order to understand that, we have a plot about it, Bode plot. Have you heard of it? Bode plot? Yes. Okay. Just remember that. The Euler identity gives us the general form of sinus cosinus signal, like this one. If we have this Euler identity, we have the imaginary components and real components in here, just like S-plane. Remember that? And also we have the magnitude of this signal M1 and we have phi 1 in here. This is the polar coordinates, right? And so every system can be represented by this form, because in S-plane we do that, right? What is the pole location? The pole location is the magnitude and the degree. In the root locus, we have the magnitude and the angles, right? This is identical. And so, any signal can be represented like m1 magnitude times cosinus wt plus phi 1. This is the phase, this is the magnitude. Okay?
I have a small question. There was a how did we used to represent the sine wave using this circle? Like there was a
This is the Euler identity. This is the frequency component. This is the basis of the frequency component is equals to the what? Euler identity. The frequency is defined by using the Euler identity formulation. Okay?
Was the frequency was the W was the imaginary part and the phase was the real part, right?
Yes. That's all. And so, if we rewrite our system, and then we can write this. We have the input signal in here, just like this one. Mi, W, and in polar coordinates, phi I, W, right? And we have a system. If this system has the S or transfer function domain, and so also we have MW and phi W, right? Otherwise it's wrong, right? Because it's on the S-plane. And so if we have the poles of this system, just like this one, it's the -2 plus minus J3, and so it has a magnitude and the phase diagram, right? What's the magnitude? Magnitude is that. And so what is the degree? Degree is that. That's it. So we can generate the output signal in here. MO, W, and phi O, W, right? And then if we have the any MCK system in here, and xt is equals to what? MO output cosinus W phi O, and also if we have applied the FT just like this one, MI cosinus W plus phi I, we will get this output. Okay?
That's the steady state.
Yes, but in the steady state we have the sinus signal, frequency signal right now. Normally, in the unit ramp or the parabolic signal, we don't have the frequency components.
It's the numbers.
Yes, constant. But in this case, it changes. Based on the what? Yes. No. Based on frequency.
So what is like a real life example of frequency input, frequency output? Like so we can relate this to real life.
If I put the signals in the watt, in this frequency, for example, it's the 2 Hertz or the 3 Hertz. And this the natural frequency of this table is equals to the 3, and so we have the resonance. Do you know resonance? Yes.
Is it really
Radios and stuff.
Yes. At each case, in the resonance case, we accumulate the energy on display, and so it will broke. Even if I put the small push, small magnitude, like this one. Okay? You get it? Do you know the resonance?
No, not really.
It's like when you have a swing, imagine you're swinging on a swing.
Yes.
You push exactly when you reach the top.
For example, if you have the pendulum, and pendulum oscillate this way, okay? At each case, the pendulum goes and pendulum says. At each case, I push the pendulum at this case, and so it grows up, right? And so, if the pendulum has the 1 Hertz frequency, and I put the one hot frequency input in here, and at each case it grows, right? Grows, grows. This is called resonance. At each case,
If you put like a 10 hertz frequency input, it'll be different. It won't grow.
maybe or may. And so, how we can analyze this form? How we can analyze this frequency damage the system or not? We should utilize frequency components in here, frequency concepts. How we can draw the each frequency affected on the system? How? We should draw the body diagram, body plot. Do you get it right now? At each frequency component with the input signal, we should draw a plot. Frequency 1, 2, 3, 4, 5, and at each case, we have the system with specific amplitude and phase degrees, which is called the body plot. Okay? Even if you have the perfect PID controller, if you apply the sinusoidal or the cosinusic or with frequency component signals, and you have this kind of response in here. Okay? And the affection of this term can be studied by the what? By frequency concepts. Just like this one.
So it's like when we want to analyze something periodically, we change to the frequency domain.
Yes, or we can change the RPID rules, or we can change our plant. We should design a new plant to satisfy these conditions. When you have a car, for example, if you start a car and so the motor spins, right? And so with a low frequency. If you push the button and so at the low speed, even if you are stopped, and so the car vibrates, right? What's the meaning of this? This motor spin frequency matches with the natural frequency of the car, and you vibrate, right? This is called the resonance. And so we need to analyze this concept based on the input signals. This is directly not related to the controller or stability. This is directly related to the input frequency and the output frequency. Okay?
So, getting rid of this resonance, this is our topic right now, right?
Yes. We should remove it. We should catch it. Or we should run it from the resonance, which is equal to the what? Wn.
Why is this required to optimize our system? Why is resonance not good if, for example, if the motor has a different frequency than the natural frequency?
Because in the car, for example, if you get a high speed, maybe your motor is 500 hertz at seconds, okay? And so if the car, each match is the car natural frequency is match with this frequency, your car is broken. You need to run away with this natural frequency in the car.
It needs to have a higher frequency than the motor, or a lower frequency than the motor.
Either you should pass or low. Huh?
It's like the wine glass.
Yes. Yes, that's another example.
It's like just a wine glass.
Yes.
An opera singer breaks it with her voice. The sound resonance matches the wine glass.
Why this is broken? Because the voice's frequency is matched with the natural frequency of this glass. At the resonance, you can accumulate the whole energy in the system.
The natural frequency we're talking about here is the
WN.
WN.
Yeah.
Everything has a natural frequency.
Yes, everything. We need to run away this frequency, but also we need to control this system. For example, if you have the Mercedes car, and so you want to go to the 200 kilometer divided by r speed, but if you're too close your natural frequency at this speed, and so your car is broken. And so we need to design our system with, for example, 500 hertz is selected the nature of your gate, just like in the PID controller algorithm, guys. Okay? This is we want to talk about this case right now. So, the output of signal. This may be equals to what? To this one. And also we have the output signals in here. And we made this kind of response, okay? So, in these signals, we have here phi I. This is the input, fuzz. But in the second case, if we multiply this system, we apply the plant, and so this phi in the frequency is collected. Phi O is equals to the what? Phi I plus phi. This is the system fuzz. This is the input fuzz, this is the output fuzz. Okay? Fuzz shifting in here. And also this is Mi, but this is Mi times M. Your system magnitude and input magnitude. And so this is the MO. Okay? Please. And so, what is the meaning of this? We can write the system. Like this one. W is equals to the what? MO W divided by MIW. These are system magnitude. And also phi W is equals to the what? Phi OW minus phi IW. This is called the magnitude frequency response. And this is fast frequency response. And so, if I want to draw this signal, I apply the different frequency to this system. And we have the magnitude in here. At each frequency, 1, 2, 3, 4, 5, and 10, we have such kind of graph. This graph called body plot. And after that, also we have the fuzz diagrams, just like this one, minus 90 to 90, or 0. Okay? We should analyze the whole system based on these informations, guys. Okay? Any question? Even if our system is perfect, said again, our system cannot respond with higher frequency. And so, what is the demonstration or the proofs of this system? This is the magnitude frequency response. If we have the high frequency in here, just like this one, see? And so it grows, but this is smallest, and so this reduced. And so this is just the low pass filter characteristics in here, okay? The time constant cannot permit us to response for a given high frequency input, guys. Okay? Okay? So, we have the calculation of this magnitude and fuzz diagrams, but let's do this for the next session. Okay?